All right, question 8, part B says to find the volume of the region below the cone, phi equals pi over 4, and inside the sphere, rho equals 4 cosine phi. So in question 6, we looked at the cone phi equals pi over 4 and saw that that was just a right circular cone that opens along the positive z-axis and forms an angle of pi over 4 with the positive z-axis. So we're looking at this cone right here. Now for the sphere, I claim that this is a sphere of radius 2 with center at the point 0, 0, 2. And to see that, well, start with the equation rho is 4 cosine phi and multiply both sides by rho, and that'll give you rho squared is 4 rho cos phi. Now rho cos phi is equal to z in spherical coordinates, and rho squared is x squared plus y squared plus z squared. So this then gives us the following rectangular equation. Now subtract 4z from both sides and complete the square, and that's going to give you x squared plus y squared plus quantity z minus 2 squared is equal to 4, and that is the equation of the sphere of radius 2 centered at 0, 0, 2. And so we see that up here in the figure. Alright, so now we're looking for the region below the cone and inside the sphere, so we're looking at this region shaded in white, and we'll call that region E. And so to find the volume of our region E, we're going to compute the triple integral of just dV over the region E. And so for our differential volume element in spherical, this is rho squared sine phi d rho d phi d theta. So to set up our integral as an iterated integral in spherical, I'll go ahead and put in the rho squared sine phi. And now for the bounds on rho, think about fixing an angle phi and an angle theta, and then we're going to let the radial distance rho vary. So we're going to start just at the very bottom of the sphere when rho is 0, and then we're going to pass through our region and then exit out at the blue sphere. So in other words, we're looking at this picture where rho starts at the bottom when rho is 0, and then here we're going to exit out on the blue sphere when rho is 4 cosine phi. So our bounds here for rho would be from 0 to 4 cosine phi. All right. Now for the bounds on phi, well, when we're on the cone, phi is pi over 4. And so then to cover the region E, we're going to have to rotate forward until we're into the xy plane when phi is pi over 2. So we're looking at this picture. So think about taking these green rays, and to cover E, we're going to have to rotate from when we're on the cone, pi over 4, into the xy plane at pi over 2 there for phi. So we're looking at these bounds, pi over 4 to pi over 2. All right. And then lastly, for the polar angle theta, well, we're just going to need to take a full 360-degree rotation to cover our region E. So in other words, our bounds for theta there are just 0 to 2 pi. Okay. So that's our integral, and so now let's go ahead and compute it. I'll first go ahead and compute the rho integral, and we're just integrating rho squared, right? Sine phi is held constant. So we get 0 to 2 pi, and then pi over 4 to pi over 2, and then we're going to get a rho cubed over 3 sine phi, and then we're going to evaluate from 0 to 4 cos phi, and then we have our d phi d theta. All right, so now when I plug in 4 cos phi in for rho, I'm going to get a 64 cos cubed phi over 3, and I'll bring the 64 thirds out front. So we are now looking at the following, okay? So we're going to get a cos cubed phi sine phi, and then we have d phi d theta. Okay, great. And now, as we've seen many times, right, this phi integral is completely independent of theta. So if we like, there's a simplification step, we can go ahead and just pull that out of the theta integral. So in other words, we can split this up as the product 64/3 times this integral of just d theta from 0 to 2 pi, and then we have this integral in terms of phi. So this is cos cubed phi sine phi. Okay, so now for this phi integral, since I have a cos cubed here and then a sine phi d phi, using the fact that the derivative of the cosine is negative sine, that suggests making a substitution, namely the substitution u is the cosine of phi. So then du would be minus sine phi d phi. So we're looking at 64/3 times this theta integral, which is just 2 pi, times the integral of, well, u cubed times sine phi d phi, which would just be minus du, and then changing the bounds, when phi is pi over 4, we're going to have the cosine of pi over 4 for u, which is root 2 over 2, and then when phi is pi over 2, we're going to get u is equal to the cosine of pi over 2, which is 0. Okay, so now just about there, we're going to get here 128 pi over 3. And then here, the integral of u cubed is just u to the 4th over 4. Okay, and this negative there, I'm going to use that to flip the bounds of integration. So they're going to go from 0 to root 2 over 2. All right, cool. Now let's do a little simplifying here. So the 128 and the 4 can simplify. So that's going to give us a 32 there and a 1. And then I'm going to plug in root 2 over 2 in for u to the 4th. So that's going to give us 32 pi over 3 times. So if I take root 2 and raise that to the 4th, that's going to give me a 4. And then 2 to the 4th is 16. So all in all, that's going to be a quarter. And so that simplifies to 8 pi over 3. And that is going to do it. All right, thanks so much.